or practice. If you improvise, you learn better. So I think that also is compatible with the whole incremental learning approach, because it's going to allow you to recruit more connections, more relations.
You were talking about how the problems between current AI technologies, where they show large data sets, millions of faces,
Yes, big data,
versus a more human-like approach where there's just one shot.
Exactly the same problem persists in AlphaGo and those chess programs. Exactly the same problem.
Exactly.
Right?
And for AlphaGo, that's certainly true. I mean, no one plays more than I couldn't count, maybe 1,000 or 10,000.
Yes, it's certainly not how
games.
a human learns to play, right?
Exactly.
You can say that.
But one thing I've been thinking about, humans do spend 24 hours a day, 7 days a week for sometimes up to 80 years doing stuff. Seeing faces. We don't expect our computer program, if they run for 10 minutes, we think they're running slow.
Yeah, so and there are some unfair comparisons there.
Right.
That's completely true, and that's why the common sense reasoning problem has baffled computer scientists for so long. Because on one hand, it looks like computers are faster than human, and on the other hand, oh well, it's just too slow. It's not working, or it's failing. It can't do something, and then it's stuck. But ceteris paribus, all else being the same, and now we can make the comparison. We should make proper controlled experiments,
right,
to get that human level comparison or benchmark right. So I think that's the general answer, right?
Right.
Yeah. Try to follow up with Peter's question, but things from a different angle. So if we take Dan's demo earlier this morning, with Sophia again, you can understand Einstein was a physicist, right?
Mm-hmm.
I wonder what would be the feasible steps if we want to apply incremental learning into this context, make it a little more smarter?
Into OpenCog.
Yeah.
Wow.
Just use the chatbot as a use case.
Actually, I think language acquisition is one of the harder tasks to achieve using a universal induction method, because the search spaces tend to get a bit large. But I think, it should be applicable if you use the right representation.
The subtle question there, to my mind, for language learning, I mean, in the OpenCog framework or in some other framework, I mean, what is the implicit universal Turing machine, universal language that you're using? Because if you use one that is especially well suited to human language, then incremental learning of language based on experience, based on sort of program space search, may well work. And if you start with a reference language, a reference computing framework that is quite different than human language, you're going to have to search a hell of a lot. So this basically comes down to the same old sort of Chomsky-esque problem of like how much of grammar is coded as a kind of inductive bias in the human brain. Like few psycholinguists anymore think that like the rules of grammar are really encoded in the brain. But then the question becomes, how much inductive bias to nudge language learning in the right direction is encoded in the brain? And that we don't quite know. It's clear a lot is, but not all, right? And so in this framework, that inductive bias is largely due to like what's the language in which you're performing the universal induction.
Well, you actually asked a billion-dollar question, but so if you can solve that, there's a lot of money in it. But my initial intuition was when I was thinking about language acquisition was somehow the structure of the models that the brain must use to acquire language must have something to do with the sequential nature of phonetics, right? So it's a sequential input-output system. So that introduces the same kind of constraints that, of course, language theorists like Chomsky had to deal with. I think linguists, theoretical linguists, will say something like, well, the universal grammar thing probably isn't the case, but we would expect something like an X-bar grammar, a very generic hierarchical kind of grammar to actually be encoded in the brain structure. There is some evidence that a hierarchical model is being used by the brain to process syntax. I always imagined that understanding was a harder problem, and I think they've obtained some very impressive results using deep learning for syntactical processing, but I'm not sure if the exact same approach is applicable to understanding. My guess would be that since that's related to common sense, that would be a harder problem there. Maybe syntax isn't such a hard problem once you do it right. But still, we have a lot of problems with understanding, I think. But we need better models, model classes. But I think the solution would be something like universal induction and those hierarchical models.
So this trade-off generality versus efficiency is really a chore, of course. And I wonder whether you know about approaches where you start with a, let's say, narrow search space that you can search through efficiently, but then dependent of the task, moves the search space itself or expands it in the direction of the solution.
Wouldn't that be a kind of an attention allocation mechanism of sorts? Related, maybe?
Well, attention is usually sort of in the spotlight model if you pay attention to part of the data.
Oh, sensory data, right?
Yes, what I mean is not part of the sensory data where you move actually your search space. Your
Yes,
operating search space.
that's definitely possible. I didn't come across such a paper, but it's conceivable, and I think it's something that humans actually do, right? So,
Exactly.
for instance, well, I'm going to spend no more than 20 minutes to fix some coffee for myself, and then, well, this seems like a really interesting problem, so I'll spend the next 2 hours working on it. So that's the kind of thing we were talking about. Yeah, I think it will be beneficial, definitely. But it is a kind of attentional allocation. I think it's a kind of temporal focus, right? So you're expending more computational resources on the problem that matters.
Well, attention, it's an analogy to attention.
It's a different in a different temporal domain. You're allocating time,
in the
right?
search space domain.
Following up on the earlier question regarding language, but this time referring to the domain of vision-based learning, evolution provides an inductive bias, for example, through the structure of the visual cortex that performs a lot of compression and preprocessing to the high-dimensional input that is received. Where would be the correct place to put this in this type of Levin search paradigm? Is that part of the reference machine or in a prior probability over program?
I think we can reliably assert that some visual primitives have evolved in the brain. So we would have to induce such. Otherwise, we don't want to reinvent the wheel. That's not the right way to build a system. So I'm not saying we have to build something just as complex as the brain, because it's quite complex. It's about half of our genome, and Cosmos knows how complex that is really, because quantum mechanics works in mysterious ways. But still, you get the idea. Maybe it's not too complex. I don't know. But there's something about the fusion of the 2.5 dimensional depth perception and tactile processing that is very tricky. We probably don't know the right representations. Not quite. But of course we can speculate that that there are primitives for all of these different modalities, like likely the primitives for 2D evolved before this stereoscopic vision primitives, but there should still be primitives for that too. And then there should be some primitives for our tactile sense or estimating distances and stuff like that. So I would expect actually a lot of primitives in each different modality. Sorry.
Two questions. The first is I wasn't quite sure if part of this theory is dealing with the abstraction concepts and the generalizations of things. I don't know quite what the right vocabulary or words are, but the building of ontologies or conceptual models which are being refined over time.
Yes.
Instead of just
Sure.
like-
That's the main goal, right?
Is that the main goal?
Yes, of course.
So is
of course.
is that a part of it? I don't quite see where the
Huh.
conceptual maps are being, or, you know, the representation of that. So,
Well, I think it's easier to see. I mean, maybe that's why it's really a great model. As in the Gruson model, it's kind of obvious, right? Because the frozen networks, you can think of them as some previous lower level concepts, and then you can think of the new transfer connections. It's stuff that binds them, and it looks just like a semantic network, so that's easier to conceptualize. But in the fully abstract theoretical model, we have the probabilistic representations in general that take care of that. So, what is an abstract probabilistic model? That's the question, right? Are there such things, such animals? Yes, I believe so. And I mean, obviously, our perception depends a lot on abstracting physical facts. So maybe something like a probabilistic representation of physical phenomena would correspond to our intuitive notion of an abstract concept. So that, I think, would be the positivist answer. It's just a short probabilistic model that covers a lot of facts with some errors. Not exact. What does abstract mean? It means inexact, right? It captures some essential properties of the object in question, but then it also makes a lot of errors. It doesn't specify so much. So that's the trick with abstraction, I think. And I think depending on the programming language used, of course, some abstract concepts are necessarily going to merge. Please.
About the gruesome model, you said about
Yes, I really like it. Yeah, it seems to be one of the most practical things here, so then you can even implement it yourself fairly easily, I believe.
how do you do this exploration of the model space? Can you go more details a little bit on that?
Well, if I remember, just
But I think that's also maybe a problem, like as Ben said earlier, with the blending, conceptual blending or so, because you have to combine these models like in a way that it helps in the general solution.
I think that obviously depends on a lot of other things. That's why I think the synergistic design is important, because it depends on the program representation you pick, and it depends on the program probability density function probability representation you pick, and the search algorithm. So it depends on everything else in the system, right? So it depends on the other choices you make. But in the context of Gaussian model, those are recurrent neural networks. So what is that algorithm doing? It uses a bunch of frozen RNNs, and it's introducing some new hidden units and connecting these old guys to new units, and then of course the output whatever, the fixed network, and then retraining. So is it making a good exploration of the model space? That's the question, right? Yeah. It could definitely be better. There is room for improvement there. Because as I said, the networks are frozen. There have been some objections to that. It doesn't freeze anything really. So, well, it doesn't seem to be the case. So, yeah.
Well, just to give an input to that, in some studies in incremental learning, the initial layers of a single network are frozen because they represent the data more, they are more invariant to the data.
Mm-hmm.
So the thing that you freeze is less data dependent. It should be more general. Do you agree with that?
Yeah, of course. It should be a matter of gradation, actually, I believe. But I don't have the full explanation for it right now. But I think there's some research there.
Perhaps you hinted at this earlier, but I thought you would imply that in your work you were actually applying some of these techniques to automate data mining. Can you talk a little about how that actually comes out in practice?
I think more interesting is how I approach the problem. It occurred to me that I perform some mental motions over and over again whenever I am programming. So that's when I started thinking about how to learn about programming. I think that's an interesting question that isn't being explored much, except in the automatic programming community. So yeah, well,
I understand. I was curious. I thought you would imply that you'd taken some of these algorithms and applied them to stuff in your work.
Oh, yes,
correctly, and I was curious about that actually.
Applications.
Yeah.
Applications. Well, we can apply it to. I'm going to apply it to face recognition. So that's one of the problems.
Are you using one of these architectures?
Yes.
Can you talk about that a little bit more? Or
Sure. The objective is to recognize faces from few examples. Because that's something that there's a technological limitation. So we could conceivably overcome that with using some of these techniques. So that's one of the things I'm trying to do. So that sort of thing means we really don't know how powerful these are.
Yeah, I'm asking because I've explored a few of these techniques in the past and run into problems. You know,
Oh,
being able to reach. all
There
those
there are
information,
problems,
so-
definitely. Actually, that's why I wrote all these different kinds of algorithms. So, and I mentioned some commonalities, some common challenges. Yeah, there might be some practical problems. My algorithm is not for back propagation. It's for, it was tested with a Levin search. So that's more like making sure the Levin search part isn't important there, right? The update part is important. Make sure that the update part does its job, given we have an adequate approximation. So and that's the kind of, I was more curious about about whether it works at all.
So you're using some kind of compact encoding of how you update a neural network, which is actually doing the face recognition? Is that the architecture?
Yes, that's the kind of thing I'm trying to do now. Exactly. It's not completed, so I'm not able to give a very definitive things. It would be dishonest. So, but that's what I'm doing.
So you're saying that you're keeping it static or it's modifying at this point, the neural network, for the facial recognition on a few instances?
I believe, one of the themes that I was trying to drive it was plasticity. Plasticity is important. So the more flexible, the more variation, the better, I think.
Okay. I'm leading to this point here, that humans were experts at certain faces and not at others. Humans are experts at some languages, not at others. As an infant, we lose the ability to recognize phonemes from other languages. In faces, we only recognize the characteristics of our own culture or those.
Of course, the racial bias, right? Confirmation bias.
Precisely.
Yes.
So that's what I'm getting at is if learning a few instances of a single face is still an expertise within a culture, kind of their common sense, let's say.
That's insightful. Yes, no, humans do have that problem. Maybe the machine won't have it, and that's very interesting because that does limit humans, right? Because some networks apparently do get frozen. That's what it really means. Or maybe parts of the brain lose the ability to recruit new resources. Maybe if we just injected some kind of neural growth factor and then immerse them in that culture, they will learn. We don't know, right? So it might be some kind of biophysical limitation to some kind of computational limitation to maybe the base algorithm is correct and complete.
If cognitive science has gone through that and has found some ways to try to assist it to acquire those phonemes or to acquire that facial discrimination within other cultures. But there's nothing that would allow it to do at the level that a machine would. If we
That's
ever get to
interesting,
that.
but I'm thinking like maybe if we somehow increase the plasticity of the elder brain, maybe it would work. Without any biochemical intervention, it probably wouldn't work. That's my that's my guess, but I don't know. That's very interesting though. That might be one thing. The machine might be very superior to a human because doesn't have the same kind of computational limitations. Thank you. I think we're